Today we will be demonstrating how we measure the speed of sounds by Enoch, Kumpel, Caleb Rains, myself, Teagan, Reid, and Tanner Walker. The objective of this lab is to demonstrate 3 ways to prove the speed of sounds, and we'll also be learning about the proper procedure for physics lab, and we will be finding and minimizing our errors. For the first activity, you'll need 2 audio recorders, a rangefinder, a large caliber noisemaker, walking shoes, and for the second activity, you'll need an assortment of tuning forks, a large graduated cylinder, some water, a meter stick, and a decibel meter. And for activity 3, you'll need a video camera, some film editing software, we used iMovie, a balloon and a push pin, and a rangefinder. The purposes of these activities is to prove or to measure the speed of sound 3 different ways. For the first one, we'll be using the equation that velocity equals distance over time. To get our distance, we will be using the rangefinder, and to get our time, we will use 2 audio recording devices set some distance d away from each other and looking at the difference between the spikes in sound. For the second activity, we will take advantage of natural resonance by making a sound at the top of a graduated cylinder. The air near the top is able to move freely, but the air near the bottom is standing pretty much still due to friction with the water. This creates a standing wave with the water as the first node and the top of the cylinder as the first antinode. The standing wave will resonate when the wavelength of the sound is 4 times the distance from the top to the bottom of the cylinder. For the third activity, we'll use a video recording device, and to find distance, we'll use the same rangefinder, and to find time, we will count the number of frames between the video of a balloon popping and the audio.
So our first activity, our method is fairly simple. Start 2 sound recorders, be able to sync the time with a distinct noise, walk however far away, make said loud noise, find the difference in time between the audio spikes on the different phone recordings. Between the averages of our 6 trials at varying distances, our average measured speed of sound is 345 meters a second, compared to the expected of 343. That gives us an error of 2.65 meters a second and 0.77%. Now, errors for this likely come from wind and temperature difference. It was very windy the day we took measurements. Relativity we did not take into account because I looked into, and at the relatively short distances for our accuracy we were aiming for, it would not make a difference.
For our second activity, we use resonance to measure the speed of sound. So we start off by pouring water into a graduated cylinder and hitting a tuning fork and placing it over the top. And we measure the sound intensity with a phone. We keep adding water, and the tuning fork, place it at the top. And since the sound intensity at that point is greatest, we take the distance from the water level to the top. And since we know that that distance equals lambda divided by 4, we can find the wavelength by simply multiplying the length of the air column by 4. We did this for 3 different frequencies and obtained velocities for each of them and got an average velocity of 337 meters per second, which corresponds to 1.78% error. That percent error is likely due to the ambient noise of the room. and also the tuning forks being out of tune.
For our third activity, we decided to measure the speed of sound using slow-mo camera and a balloon. So we set the balloon up a certain distance away from the video recorder, and we just started the slow-mo and popped the balloon. We then took that video and uploaded it to a software we use, iMovie in this case, and we separated the audio from the video, and we zoomed in really far to get frame by frame, and we then found the exact frame at which the balloon disappeared and the exact frame at which there was a spike in the audio where the sound reached the phone. And we counted the difference in those frames. Here we have, for the first trial we found 9 frames, second 12, for the third 10, and so on. And we took that amount of frames and divided it by the FPS of a standard iPhone, which is 240, to get our time. And using then the standard equation of V equals D over T, we found our velocity, and we did that for 6 different trials and averaged all those velocities to get a measured velocity of 382 meters per second. The expected is 343 meters a second, giving an absolute error of 39.2 and a percent error of 11.44%, which is higher than our other activities. This is likely due to the fact that we were working with a relatively short distance compared to the speed of sound, and the FPS is not as high as we would like it to be, but it is all we had access to at the time.
So to recap, our percent errors for the 3 activities were 0.77% for the first activity, 1.78% for activity 2, and 11.44% for activity 3. These errors being so low suggests that our methods were viable and that we accurately measured the speed of sound. Some applications for why we might want to know the speed of sound in physics is sonar for tracking things underwater or even in air. The speed of sound is very necessary when reflecting sound waves off objects. Additionally, when creating objects like military planes that may fly faster than the speed of sound, that threshold needs to be known because extra precautions need to be taken for vehicles that go that fast. Thank you.